forget all the lines.
I forget my lines all the time.
Just go with the flow.
Say whatever.
Yeah, then you need to
Long
spot it.
Greek name for you,
Yeah.
you die.
But yeah.
My name is Alexandros Papadidios Kriatos. If you remember, this contains some transparent liquid. It looks like water, but it's actually not water. It's actually a solution of concentrated sodium bicarbonate. So that's actually a bit alkaline. Alright? And in the second container here, wine glass, there's actually a little bit of acid-base indicator, which is called phenol phthalate. It's acid-base indicator that I don't know how to pronounce, right? But it's red, it turns red when it's alkali and it's transparent when it's acidic. So when we pour this over here, it turns immediately to this nice red color, rose syrup kind of color. Okay? And the next thing that we did was we pour this over to here. Now if you remember, we have carbonate originally. And in this container originally there's some bit of barium chloride. Okay? And once that's dumped over, the carbonate immediately replaces the chloride to become barium carbonate. Now, barium chloride is soluble in water, barium carbonate is not, and hence it precipitates out, and when it precipitates out, it looks like milk. Now you can see that it's actually all settled, it's not really milk. So I'm going to explain to you now how these magic kind of like a reaction work. It's not really a very complicated reaction. Okay, what actually happened is you're essentially seeing hydrogen peroxide break down in water, H2O, and oxygen. Alright, so H2O2 is a molecule, it's kind of like water but with extra O inserted. And the reaction essentially is the release of this O. Under normal circumstances, it takes a long time, okay, for the oxygen to be liberated. But if you add something called a catalyst, things happen really fast. And that's this thing that I poured in. That was potassium iodide. Now, and once we poured it in, that reaction happens really fast and it generates a lot of oxygen suddenly. Now, we also put in some soap detergent and some coloring. And that's what makes up all this bubbly thing, which is actually just normal soap bubble that you can play with in your kitchen sink. And that's it. So the explosiveness comes from the sudden release of a lot of oxygen, generating a lot of soap bubble and throwing things out in the air.
So the explanation of the drinking game is based on the mathematical notion of an invariant. So invariant is a quantity that does not change. Like the invariant of the drinking game is the number of cups modulo 4. Right, so in the beginning it was 13, which is 1 modulo 4, and in order to win I need to make sure that it's still 1 after my opponent's move. So what I do is after I make sure that after all after two moves together, it remains 1 modulo 4. So the number of cups that I'm drinking is 4 minus the number of cups that my opponent is drinking. And then it was 13 in the beginning, then 9, then 5, and then finally it is 1. Now, the explanation of the card trick is kind of, if you think about it, is kind of natural. So because strictly speaking, it doesn't work all the time, but it works most of the time. So it works like 80, maybe 85% of the time. So the deck of cards that we played with is actually a random thing. So we didn't arrange it on purpose. And the reason is because, so imagine that it's just, I don't know, let's say if you have 3 in the first row, and then you count 3, and then you still are in the first row, and then suppose that you count 3, and then you arrive at, I don't know, at a king. So then the 3 and the king are going to end at the same final card anyway. So which means that just by randomly, some cards in the first row are going to lead to the same final answer. But then imagine that you had 2 different cards in the first row, but then they lead to the same card in the third row. Then after that, they're still going to lead to the same answer. So no matter which row, they just by randomly got to the same card, the final result is still going to be the same, right? And then let us just try to get some rough calculations. So suppose that, so in the beginning you have 10 different choices in the first row, and suppose that after every row, just by random reasons, the number of cards, the number of different possibilities in every next row is 2/3 of the number of possibilities in the previous row. Then it means that in the beginning there were 10 different possibilities, but in the end, after 5 rows, it's going to be 10 times 2/3 to the power of 5. And then times 2/3 to the power of 5 is about 1.3, which means that on the average, we are going to get 1.3 possibilities in the last row, which means that, well, 1.3 on the average. It means that 1 is more likely than 2, and 1 is more likely than 3, and so on. So it means that usually we are going to get 1 in the last row.
The reason for why the magic tricks work is due to the law of physics. Basically, it is the laws of Newton, where torque is equal to the rate of change of angular momentum. So in both cases, there's a torque acting, and because of the torque, there's a rate of change of angular momentum. So I'm going to show you the example through the drum going up the hill and also the bicycle gyroscope. In the drum, there's a piece of weight that is hidden inside, and this additional weight actually causes a torque that leads to a change of angular momentum. Yeah, here is the bicycle gyroscope with the bicycle wheel. So if we were to tilt it up, there's a torque, R cross mg, so the torque is pointing towards me, and it will cause the wheel to rotate down. Okay. Now the interesting thing is, if we were to spin the wheel, and the rate of change of angular momentum will follow a vector rule, and you will see that it will precess and defy gravity. So that's good. So the torque is still in this direction, but the angular momentum is along the axis of the wheel, so the torque causes it to precess. And that explains how it works.